So anyway, now that I know the audience better, I think it's ridiculous to go to this slide, so I'm not going to tell you what the sign problem is. And I'm not going to even tell you when it appears. It appears everywhere. It's an important problem. And even if you restrict to XQCD, there are at least 3 circumstances where it appears. Of course, for people like me who started out in this business by actually doing phenomenology and XQCD, not numerical calculations, it's this one that matters. But you heard a lot of talks about computing transport coefficients and things like this and the relevance for weak physics. We usually don't talk about this because it's such a non-starter that we don't even connect the fact that computing transport coefficients and the sign problem are one and the same problem. Anyway, I will spend 5 seconds telling what reweighting is. So, if you want to compute a certain observable field theory and your action is complex, you have the issue that was discussed repeatedly here, right? One way of dealing with the imaginary complex action is to take the imaginary part as part of your observable and just rewrite the observable as a ratio of this quantity, the observable times the phase, divided by the average phase. And as that's well known, this fails miserably because this quantity here, down here, is exponentially small, both in the large volume and in the low temperature limit. So that's a form of the sign problem. I will be using some forms of reweighting like this later, and that's why I want to point that out. Now, this central idea, as you pointed out, is instead of integrating over real fields, as we usually do, we can deform the contour in complex space. Okay? So before you say that the sign problem is going to come back some other way, miraculously, let me give an example where it obviously doesn't. Let's take this Gaussian integral here. Right? If I try to compute this integral on the real axis, I get this thing. And to compute this right value here, I need the cancellations of the other one part in 10 to the 70. However, of course, this integral here is the same as the integral over this other straight line here. Over the straight line, this integral is computed by I and gives you the correct answer. Okay, so that's a sign problem that's completely solved. It's proved by demonstration by an example. Okay. Of course, the integrals you're going to compute are a little more complicated than that, but that's the basic idea. Actually, let me point out one thing. Why is this integral here the same as the one here? Like in high school or college or whatever we learn about this, the issue was this annoying little arcs that you had to worry about infinity, right? The same thing is going to be for us. So for the Gaussian, it's very easy to show that these little arcs at infinity contribute with nothing, but it's not always the case. So for example, if you take an integral that is slightly more complicated, oh, this is a horrible color. You cannot really see here, but there are some darker areas. It turns out that if you take your contour to either start or both start and end in one of those darker directions that you can barely see, your integral is well defined. The action goes to infinity, the integral goes to 0, and you're good. If you try to make a contour where the integral goes, the contour goes along this direction, the action does not go to infinity, the integral is not even well defined. Now, so you see what happens. Any contour that goes from one region and go to this other here, it doesn't matter what it does in between. It's going to give me the same integral by Cauchy theorem. However, if I try to switch from a curve like this, say the real axis, into something like this, that starts but ends in a different direction than the other one, I get a completely different answer. And that's essentially one way of thinking about it, is that this integrand here has a pole at infinity that you're crossing. But in one dimension, one complex dimension, this is completely trivial, and as I said, it's something you learn in high school. In our case, this is going to be a little more complicated. So keep that in mind. Now, what I want to do is to have my real space is the space of fields. That's going to be a bunch of real numbers if I discretize them. Typically about the order of millions sometimes, right? Now I'd like to find a different contour, maybe another n-dimensional manifold, embedded in a space of n complex dimensions. You start with n real dimensions, you find another manifold that has n real dimensions that's embedded in n complex dimensions, or 2n real dimensions. And the question is, what would be a good choice of contour? Right? I know that so first of all, I have to find a contour such that the integral is the same. So I don't cross any poles at infinity. The other, I would like to have the integral over this contour to be easier, to have a milder sign problem than the original one. So one way of choosing this is the following. Consider the flow. That's the flow that you was talking about. It's basically the gradient of the action with a complex conjugate on top. You take the complex conjugate, you have the drift term of the complex conjugate. But I like that complex conjugate. And the reason is the following. If I split up this equation here into its real and imaginary parts, I can see that this thing here is just the gradient flow of the real part of the action. So if I follow the flow, the real part of the action grows monotonically. Now, because of the Cauchy-Riemann conditions, I can always write the same equations as this sort of Hamilton-like equations, where the role of the Hamiltonian is played with the imaginary part of the action. That proves that along the flow, the imaginary part of the action is going to be constant. So the real part grows, the imaginary part stays constant. And then we say, why are you doing this, Paulo? That's the worst thing you can do. You want to solve the sign problem. The problem is the imaginary part of the action. You should do the other way around. You should try to decrease the imaginary part of the action, right? But no, trust me, this is that's the good idea. The point of keeping to follow the gradient flow of the real part of the action is that look at the value of the action towards infinity. Since this integral originally was well defined over the real field, the action has large values here at large values of the field. But as you follow the flow, that point is going to be mapped into a point that has even a larger value of the action. So consequently, the integral is going to still be even better defined. So at all points of the flow, if I take the whole real space and I deform according to the flow, I'm going to find a different manifold where the integral is perfectly well defined. So I never leave the region where the integral have a different value. So if I follow the flow, I sort of guarantee that to find a manifold for which the integral is the same. What's not obvious is that the integral is any easier. So that's going to require another slide. So what happens with this flow is the following. As you take the real plane and you evolve it according to this blue, that's the flow, it's going to get stuck on critical points, namely point where the gradient is zero. Now, along those points, since this is a holomorphic function, there's going to be n directions such that the action grows and n directions where the action decreases. So if you follow along the directions where the action grows, we have what is called a thimble. It's a bad translation from the French. It doesn't look like a thimble at all. I don't know why it's called a thimble. I tried to draw those figures with actually a thimble and it doesn't work. Anyway, we stuck with the name, so that's the thimble. Now, what does that says to you? Well, let me show you the other picture. Maybe that's better. So typically, we're going to have more than one thimble. And by more than one, I mean e to the millions thimbles. Okay? I have two in this figure here. And what happens with the flow is the following. If I start from the real space and I evolve it, the action, remember, grows. So these points are typically going to search for points where the action goes to infinity. It's very large. Now, since the thimble is tangential to the flow is tangential to the thimble, the imaginary part of the action along the thimble is fixed. But since the flow conserves the imaginary part of the action, it means that only one point or an infinitesimal region in the real plane is mapped by the flow to a region that's very close to one thimble. But the way I imagine, I try to make a move, I fail miserably. Imagine the real plane here evolving, getting like a melted plastic thing and approaching the different thimbles. The more you flow, the closer you get to the thimble. But you never cross a thimble because the flow is tangent to the thimble. You can never cross it. Now, if there's more than one thimble, there's going to be another region here that if I flow enough, is going to get very close to that thimble. Now, look at the action, not evaluated at the real plane, but the action evaluated at its image by the flow. The action here, meaning the action over there, is going to be huge. The only regions in the real plane where the action is going to be mapped into, the action of the mapped point is going to be small, are the ones that correspond to points that get close to the thimble. So those are the only ones that need to be sampled. Before, the action, was more or less uniform. I had to sample all those points. They had different imaginary parts. I had a bad sign problem. Now, if I flow enough, only a tiny little region is going to be mapped. Is going to have a small enough action that needs to be sampled. Consequently, only the imaginary part along this tiny little region matters. So if I have only one of those, the sign problem is solved. If I have two, well, if there is a perfect cancellation, then there is a perfect cancellation. But typically, it's not going to happen. Right? So that's how you try. That's how you make money out of this. Now, there are many attempts. I'd say that everybody that's not living in Washington D.C. now attempts to approach this problem by actually finding an algorithm that starts on a critical point and somehow evolves along the thimble. And that's extremely expensive because it's a difficult thing to do your updates along the thimble. Our route is going to be slightly different. Our route is going to be, forget about the thimbles. I'm going to take my real plane, I'm going to evolve somehow. If I evolve a lot, I'm going to get close to the thimbles. If I evolve a little, I don't get close to the thimbles. If I evolve too little, I don't ameliorate my sign problem. If I evolve too much, what's going to happen is that the different regions that are mapped to different thimbles are going to be isolated by enormous potential barriers or action barriers, and it's going to be difficult to sample them. So what you try to do is to find some middle ground where you can make some money. So the equations, the algorithm is this. Every point, this is not the thimble, this is some manifold that's obtained by flowing the real plane. Right? I rewrite my observable in terms of this ratio here. There's some amount of reweighting. That's the imaginary part of the action. Not here, that's enormous. But over there, it's very mild. There's also a Jacobian that appears when you transform, when you go from these variables to those variables here. This is a complex number. The absolute value corresponds to how much this is stretched, and the phase corresponds to how much the direction bends in the imaginary direction. That's by far the most expensive part of the calculation, and all algorithmic effort is invested in not doing that somehow. So my algorithm is going to be this. It's just a simple metropolis right here on the real plane, except that the role of the action is played by the real part on the faraway point, including the real part of the Jacobian. So let's test it out. So the first example is kind of a workhorse in this business. That's the 0+1 theory model. Do not be impressed. This is a 4-level quantum mechanical system. It's exactly solvable. But you learn a lot by doing those things. So first of all, if you just do it in the real plane, there is a sign problem. As soon as you get to interesting news, your phase is 0. So you need to do something about it. So we apply exactly the same algorithm. Now, there's something that can be done here that, let me show you here. This space has many dimensions. After you discretize a path, it has many dimensions of it. So I'm going to look at a particular projection that corresponds to the average field, just to make pretty pictures. That's all. It has many critical points, but in particular, there is a critical point. This is one thimble whose tangent space is just parallel to the real axis. So instead of flowing from the real plane, I can just do something simpler that started out from here. It's obviously giving the same integral as the real plane, so I might as well start here, right? It requires no computation. That's what I'm going to do. And then I evolve. And I evolve by a certain amount of flowing, and that's the result I get for, say, the analog decoupled condensate. Looks good, right? Except it's not. If you look very carefully at the deviation, there are points where you are 20 sigma away. That's the beauty of toy models. You can beat the statistics to death. Okay? So this is just wrong. Okay? This cannot be right. And the explanation for this is because, well, as you was pointing out, there are other thimbles. And they do matter in this particular case. So in this case, that's a fermionic model. There are many critical points, each one with its thimble. These thimbles are finite. They end at a point where the effective action is infinite. And they correspond to the fact that the Fermi determinant can be 0. The integrand is well defined. This is a zero of the integrand, but it's at the point where the effective action is infinite. Okay, that's the structure of the thingos. Okay. When I start from this tangent plane here and evolve a little, I get this surface. That's the same, gives the same integral. I can evolve a little more and get another one. I can evolve a little more to give another one. So it's approaching the thingos. Okay. That previous calculation was done with a lot of flow. So basically, I was integrating over a surface that's very, very close to the sum of the thingos. And by the way, you see that this algorithm finds exactly the right combination of thingos corresponding to the exact integral. So that what this suggests is this. Well, don't do that. The integral over this tangent plane here should give the right answer. So just do that. If you do that, you get these blue curves here. So where it was deviating by 20 sigma, it doesn't deviate anymore. So that's a case where actually doing an integral over the tangent plane this is not an approximation to the real thing. This is exact. Except that the sign problem is a little worse. But in this case, it's a little worse, but it's not bad. So we can deal with that. This way you can approach the continuum limit, and you get the right answer. If you try to go to the zero temperature case, it's a very boring curve for the condensate. There is only one point here that's interesting. The integration over the tangent plane there's a bad sign problem. So what you do to fix it, you flow a little. So actually what happens is this. If you integrate with zero flow, and you integrate with tangent plane, and you do a histogram of the average values of the field, you get this curve. And if you look at the imaginary part of the action, you see it's very distributed over minus 2 pi to pi, so there's a bad sign problem here. That's why getting a big error bars. But if you flow a little, you see the regions in the tangent space that are mapped into the different thingos. So you're sampling all the appropriate thingos automatically. In this case, 5 of them. And of course, the action varies much less. It's concentrated on those peaks. If you do this, you get the right answer. After you get happy with 0 plus 1, you start getting more ambitious, you start doing field theory. This is just a preliminary result. I'm not going to show you the real thing. I'm just going to show you a small lattice. There's a lot of algorithm developed that's relatively trivial to be done, and it's being done. But this is simple enough that I can do it in this stupid way. So here I show you first the results of computing the density as a function of the chemical potential, and the phase, the average phase, as a function of the chemical potential. Again, it's hard to see the yellow dots, okay? But what you see is that if you do the integral of the real plane, the usual real rating, as soon as mu is of the order of the mass of the fermion, you get 0. I mean, there's no way. It's a really bad sign problem. And in fact, as soon as you get there, your errors go crazy. But then you do something a little smarter, that you just shifted by a constant. Translate over your space. Integrate over the tangent space of one of those symbols. It's a perfectly good surface. The sign problem gets much better, and your results get much better. But eventually you get a mu where the sign problem comes back, and your errors go nuts. So what you do is start there, and you flow a little. Not a lot. You don't want to be too close to the thimbles, just a little. And that's what you get. The sign problem is gone, and you get smaller bars throughout the region. Now, I expect that as you go to larger volumes, you're going to have to flow more. As you flow more, you may be in a situation where you have contributions from pockets. And doing Monte Carlo in that situation, well, there are algorithms that can do that, but it requires a little more sophistication, so you don't get trapped in one of those pockets. Just to finish it up, everybody knows why I want to compute observables like this. They're real-time things. Okay? Almost nobody does that because, I mean, it's a non-starter, right? The whole action is the imaginary part of the action, the exponent, right? So there's a formalism to do this in equilibrium. Even out of equilibrium, you can generalize this. That's to do regular field theory in real time, and then backwards in real time, and then a little bit along the imaginary action. It's a well-established formalism that people use in perturbation theory. Now, this is the worst sign problem there is. Just 1 minute, I'll finish. Because if you are at one point right here, and you do some metropolis and you change the value of the field at that point, the real part of the action, meaning I times the action, doesn't change at all. So there is no damping. So you compute this sign. You don't get a sign that's exponentially small. You get 0, exactly 0. But so what? What I can do is, again, we start from the real plane. Don't try to be smart and find some tangent plane to anything, but they are in a different homology class, you get the wrong result. So just do the stupid thing. Start from the real plane, flow enough, and in this deformed surface that I cannot even imagine, do the integral the way I told you. Okay. Without giving any further details, I just flash transparency again. The only thing I want to point out is that the only time this was done before was with complex Langevin. And my understanding is that the problem was when the maximum time here was larger than the inverse temperature, Langevin seemed to go to a different place. I have no understanding why, but this does not happen. This maximum time is 3 times the inverse temperature. And that's what it is. Thank you.
Okay, sure, there are questions?
Just I don't know how relevant it is because I didn't see it.
Yeah.
But at the beginning you rewrite the evolution equation assuming Cauchy-Riemann that is for holomorphic.
Yes.
But at some moment you had Paul. How do you manage this? You stay away from them or
You stay away from
Paul, the zero of the mirror.
Oh, no. That's... Okay, so let me see if I can... So the evolution is going to stop at one of those points.
Okay. This
So
is
you never have to go past that.
Okay, so you stay away from the singularity.
Yeah, the flow automatically is not going to go there. So
But how do you do that in a complicated model like lattice QCD?
well, this has all complications that you can imagine. The complication here comes from the points where the determinant is 0.
Yeah.
That's why you don't want to sample it, right?
Yeah, but
This has the same thing here. There's nothing
so you
like
have to calculate the determinant all the time and to shift the...
That's a separate issue. I mean, how to make the determinant fast. So basically what we're doing is to develop any kind of pseudo-formulas to do that. Now this calculation that I show you was actually doing by inverting the matrix because it was small enough. But that's just laziness.
Good.
So you throw a little bit into the complex plane, basically. So this is a property of the drift, then, that you don't flow away, that it stops?
Well,
So how do you control how far it's obviously determined by
so
the...
if you flow an infinite amount of time, you evolve until you hit all the relevant symbols and you stop. That's because the flow is tangent to the thing. In fact, the fact that my real plane evolves into a certain combination of symbols is what you call the intersection number. So that part is automatic. The algorithm just finds the perfect combination of symbols for you, and it's not going to cross.
How do you know
When do you know how to stop? Well, you try not to flow at all, and then you see a sign drop. Then you flow a little. It costs money to flow, and then you flow more. At some point, your sign problem is mild enough that you say, good enough. And there's some trade-off between statistics and flow here.
Actually, there are cases in which if you flow out of the main tangent space, you find direction by which you go.
Oh yeah. The real time is like this. The real time...
No, this is simply to say that to some extent you always need some understanding of the homology class.
Now, see,
Yes.
in the real time, for example, I know nothing.
No,
it's
no,
too
no.
complicated.
Even in the simple one-dimensional cases, there are cases in which if you flow from
Yes.
the original path of the integration, you're exactly fine.
Yes.
If you flow from the
Yes.
tangent space
Yes.
at the critical point, then you
Yes.
are not.
So that's why we don't do that. We don't flow from the tangent plane unless you have a good reason to believe it's right.
Yeah, I mean,
we usually don't.
Yeah, but there are other cases in which, in many dimensions, things become trickers. I mean,
What I'm saying is that you never have to do that. You can always flow from the real plane. This real time is done like this. We try to flow from the tangent plane. It's very clear it's wrong.
Not in any case. I think now you have the chance to continue on your own. So, Francesco?